So let me briefly go over what we were doing last time. Are there any questions before we begin? How many of you haven't submitted your homework 5 yet? Okay. Um, so yeah, the submission is open till tonight 10 p.m. And if you can make that deadline, there may or may not be a very small penalty. So, yep, may or may not. um, sure. Um, so, uh, is your code not working yet, or what? Oh, okay. All right. Yeah, question. It doesn't grab the edge loads? Oh, really? Okay. Uh, okay. Yeah. Have you posted that to the forum or something? No? Okay, I'll make sure I'll correct that. Any other points or something? Did anybody try it with an input file that has edge loads? You did? Oh, okay. Okay. Cool. All right. So what we were doing last time was trying to figure out uh, what is the appropriate order of quadrature that we need to be able to integrate all these quantities in our stiffness matrix and in our load vector. So there's a note that I've included for today that you should add to right after these couple of pages. So this first page from today's lecture notes, that's the note on full integration. This note should actually go along with this appropriate order of quadrature. So the reason is that last time when we were talking about this uh, integration of B matrix, and we said that B matrix is linear in C and in eta, this holds true. These are all approximate. These are all approximate estimates of what this proportionality is, and it is under the approximation that that the element, this deformation from the parent element to the actual element in the mesh, that this deformation is not going to distort the element. Okay. Uh, so what we mean by distortion is that if you start out with a square -1 to +1, then it should not distort to something like a quadrilateral. It should not distort something like this. If it distorts to a parallelogram, then the J is your determinant. What it measures is how much is the change in the domain, in this case change in the area at each point of this quadrilateral or of this square. So if you take this square in the parent element and you map it to a parallelogram in the actual mesh, then you can show that the J, that is the deformation, this is the change in area point-wise, is actually uniform. Um, and since J is constant all over this area, then all these estimates that we came up with last time, like that B matrix is linear in C and eta and all that, they are valid as long as your J is almost uniform. Another reason is that if you take a look at the form of the B matrix, and let's see if we can pull that up. So this was the form of the B matrix. And clearly the B matrix depends upon the derivatives of the shape functions with respect to x and y, right? It does not, these derivatives are with respect to x and y and not with respect to the parent element coordinates. So there are certain tricks that people have used and come up with all these estimates of what these quantities are proportional to. So this thing, like we said last time, that B matrix is proportional to C and eta, and the J matrix, the determinant of that J matrix is linear in C and eta. So the integrand turns out to be cubic, and what we need for full integration is 2 cross 2. So this is again an approximate estimate of this. Um, so another note, I don't know why this keeps, okay. Um, so I've already mentioned this, that these are estimates when j is constant. And now if you restrict that the j is the change in area point-wise from parent element to the actual element. If you restrict that this j has to be more or less uniform throughout the domain, then it causes some restrictions on element quality. What does that mean? It means that if you make a mesh of a two-dimensional domain, then you should not have any elongated elements like this. In this case, j is going to tend to 0 as you shrink the height of this element. So what does J measure? J measures the area, the change in the domain when you go from the parent element to the actual element. So in this case, as you shrink it down, the area goes to 0, and this leads to a lot of numerical errors. So this is not a good choice to make when you're making a mesh. You should not have any elements that are very skewed like this. Another type of bad element is if you have any elongated rectangles. So something like this. If you have an elongated rectangle, that is also a bad element in a mesh. Even though for these all three of these types of elements, you can see that J is going to be uniform. Everywhere you go from this point, anywhere in this parent element, you map it to its corresponding element. The value of J at that point is going to be the same everywhere. So even though it is uniform, this is not a very good element to create in your mesh. Another bad type of element is this, where you are mapping a square to a quadrilateral where one of the angles is more than 180 degrees. So what happens in this case is that if you, let's say this is the corner that gets mapped to a reentrant corner. So what happens is that the value of J in this quadrant will go negative, meaning that this is something like if it were a physical problem, what this means is that you have crushed the element into itself and gone negative. So that J, whenever this J matrix, or this is the Jacobian, if it turns out to be negative, that's also not a very good element to have in your mesh. Um, so obviously all these restrictions are fine, but whenever you make a mesh in a finite element program, maybe using Abacus, you will end up like these types of elements. And these types of elements are not parallelograms. And since there are not parallelograms, therefore J is going to be approximately uniform as long as you say that, as long as you make sure that its aspect ratio is small and the distortion due to isoparametric mapping is small. Now what does small mean? It's a very subjective measure. So this is mostly that saying that you want to keep your elements which have nice aspect ratios like this, and they are not too twisted or elongated in one direction. Okay. But in general, when you have these kinds of things, you are going to have distortions. And if you try to find out what is the form of the B matrix in that case, then you will see that the B matrix, which contains the derivatives of the shape functions with respect to x and with respect to y, we saw that these derivatives we can calculate using J inverse transpose. Now this is a 2 cross 2 matrix inverse transpose times our derivatives of the shape functions with respect to the parent element coordinates. So this is a little bit of a math, but the distinction here is that now this is also an important relationship. So you have to calculate your derivatives with respect to x and y, meaning these x and y are the real coordinates. If you want to calculate the derivatives with respect to the real coordinates, you will take your derivatives with respect to the parent coordinates, and you will apply this J inverse transpose matrix to that. And if you write out what J inverse transpose or what J inverse is, you will see that this is the J matrix. This is nothing but your just like your deformation gradient matrix. So this is dx by dc, dy by d eta on the diagonal, and the off diagonal terms are just coming from your x by eta and x y by c. So if you take the inverse of this, we know that you find the determinant, put it in the denominator, this goes here, and the off diagonal terms just switch the signs. So that is your inverse of a 2 cross 2 matrix. But it also happens, especially for all these kinds of one-to-one maps. So this is a one-to-one map. Each point in the parent domain will map to a point in the actual domain. And it so happens for these kinds of maps, this matrix inverse, you can take the element inverse here. So this is dx by dx, and this is dx by dx. Similarly, this off diagonal term goes to this place. So essentially, what we are saying is, if you were to write it in a initial notation, that if your J matrix inverse of I comma I, this is a initial notation that is instead of saying I comma j, I'm writing it as big I comma I. This is also a common notation in continuum mechanics. It is equal to 1 over j I comma I. So what we are saying is that if you're trying to find out the components I comma this I big I comma small I of the inverse matrix, they are nothing but the 1 upon the component of the original Jacobian matrix. Okay. So it is this relationship actually which allows us to simplify the form of the B matrix, and that's why all those error measures or all those orders of approximation that we came up with last time were giving you valid results. So if you have distortion in your elements, then for general Q4 elements, you will see that once your element stiffness matrix, you write it out in your parent coordinates, then you will see that each of those terms, so for example, B matrix is going to be J inverse transpose times this. And what is that quantity? This quantity is going to be proportional to this quantity is going to be proportional to C. Why is that? Is that okay? So let's go over this slowly. B matrix is derivatives with respect to x and y, which is going to be J inverse transpose times the derivatives with respect to xi and eta. So if I give you shape functions with respect to in xi and eta coordinates, what is the derivative? What is the order of the polynomial of this derivative? If it is a Q4 element, it is linear in xi and linear in eta. And if I take derivative with respect to xi, what I'll be left with is eta. Right? So this term is going to be proportional to eta, and this term is going to be proportional to xi. And and there is this J inverse transpose sitting outside, which is all this term. So similarly for this term, this is nothing but your sum of the shape functions with respect to taken derivative with respect to eta. So this is also proportional to xi, that's right here. This is going to be proportional to xi right here. This is proportional to eta because this is a derivative with respect to xi, so that's right here. And similarly, this is proportional to eta. Now we are doing a B transpose B dB, so we are actually multiplying B with itself if D is constant. So that's why there is this square outside, and that's why we also have this 1 upon J square outside. And if you take this quantity, which is right here, multiply it with J, then this J and 1 of the square goes away. So this entire thing is going to be proportional to something that is quadratic in C and eta in the numerator, and it is going to be proportional to J, which is in the denominator. So this actually becomes a rational function. There is a polynomial, a quadratic polynomial in the numerator and a linear polynomial in the denominator, and they may not cancel out. Okay, so you cannot say that, well, C square and eta square in the denominator and C and eta in that in the numerator and the denominator, you cannot cancel out powers like that. So since this is a rational polynomial, there is no Gauss quadrature rule that will integrate this quantity exactly. So, so what that means is that even if you wanted to calculate this integral, what we want to calculate is this integral for our element stiffness matrix. If the element is distorted, we cannot calculate this integral exactly. So there is no such thing if you want to strictly say that there is no such thing as a full integration rule. So all those estimates that we came up last time, let me mark those up. So you might want to mark this, that this is a convention that people say for a Q4 element 2 cross 2 is full integration. Similarly, last time we also said that if there is no element distortion, the full integration rule 4 cross 4 for a Q9 element, that is also an estimate. There is no such thing as a full integration rule for when you have element distortion. Now in some of the books actually you will see that instead of 4 cross 4, they list the full integration rule as 3 cross 3. But that is also questionable because again, there is no such thing as full integration. So and there are actually, these are sort of complicated issues to decide what is a full integration rule. But what is certain is that this thing that we were talking about last time, the minimum order of quadrature that is required is that will integrate the Jacobian exactly. So the minimum order of quadrature that is required to maintain convergence is that your Jacobian has to be integrated exactly over the element. So this reduced integration rule, that is correct, and that will maintain your convergence. Okay. So yeah, in general, you have to keep in mind that all these integrals, all these k element matrices, these integrals are going to be rational functions. Gauss quadrature cannot integrate all these rational functions exactly, and we don't even need to integrate them exactly. So if you choose a higher order Gauss integration rule, you will be integrating this integrand more accurately, but it will still not be exact. Okay, so that's the small note about full integration. We've already talked about the consequences of what are all the consequences of reduced integration, and then we also saw last time how to do some post computation, where essentially what we are doing is we are calculating all these B matrices and the stress quantities after you've found all the solution. You go back and calculate your B matrix at each of those Gauss points, and you find your stresses there, and you interpolate them. Yes. In this case, so if you calculate this determinant j at different points in this parent domain, it will be it will be different. Do you,
It means that in different location it would be the same value, you said?
right. So when I say that j, yeah, when I say that determinant of j needs to be constant or needs to approach uh, to be a constant, what that means is that the deformation uh, the deformation at different points of the parent element. I'm not talking about the actual deformation of the mesh. This is the deformation from due to the isoparametric map. This is the parent element, which is something fictitious that we constructed, um, and it maps to the actual element in the mesh. This is an actual element in the mesh which has coordinates all these 1, 2, 3, 4. So this j is going to be when I say that this needs to be constant or needs to be uniform, what that means is that if you go from any point here to the corresponding point there, you will see that j can be different at different points. And one example of that is right here. If you map one point from here to a general quadrilateral which is not a parallelogram, then the value of j at different points is going to be different. So just try to imagine if you have a square plate, and if I stretch it in different directions, then the point-wise strains and stresses are going to be different. If I started out with a square plate, and if I stretched and map it to this quadrilateral plate, then the change in volume, the strains, the stresses, all those kinds of things are going to be different at different points. So that's also the j. J matrix is nothing but your deformation map that is going to be different at different points. So all those estimates that we were talking about last time for full integration, they are valid only if this j is almost constant. And almost constant is a sort of a mathematical way. There is a lot of mathematical theory behind that almost word, but we are not going to go into too much detail about all that analysis. So what I'm saying is that you can accept that the full integration rule for a Q4 is 2 cross 2. The reduced integration rule for a Q4 is 1 cross 1. I'm not sure if that answers your question.
And what is your criteria for the distortion? I mean, if you have a distortion that when the determinant J would be uniform.
Um, so when you construct a mesh, you want to construct a mesh that has minimum distortion. That is, all your elements should look as close as possible to a parallelogram. When you construct a finite element mesh, your elements should look like parallelograms. But um, this condition, what is the minimum order of quadrature required? This is something that this is something for people who write finite element programs. So if you were to develop a new element instead of a Q4, let's say if you are developing some Q20 or something, a huge uh, a huge element with lots and lots of nodes, then you would want to make sure that it integrates the Jacobian exactly. That's the condition that makes sure that your finite element mesh with a new type of element, if you make up a new type of element, that would converge. So these are all estimates again, that what is the full order of quadrature that is required to integrate these element stiffness matrices exactly. But again, these are you cannot integrate the element stiffness matrix exactly if there is distortion. So these are just rules of thumb that you have to accept right now, because there is a lot of mathematical theory behind that. The full integration for Q4 is 2 cross 2. Reduced integration is 1 cross 1. Similarly, for higher orders, we'll see that for Q9, as I said, it is 4 cross 4. The reduced integration is 2 cross 2, and so on. But anyway, so all right. So last time we also took a look at these these consequences. So one of the first consequences of reduced integration we saw was that it will increase your computation speed. Um, and we also saw that it will lead to superconvergence if you calculate your stresses at what are called Barlow points. Barlow points are one order less than your full integration rule. So you calculate your stresses at the midpoints of these elements and average them out. That will lead to superconvergence. And then we saw that in general, finite elements are stiffer, and if you want to, if you use the reduced integration rule, it makes your response softer, and that is a little more accurate than the full integration rule. And this is about where we stopped last time. So let me make this point again here. Um, for the Q4 element, your element stiffness matrix is going to be 8 cross 8, which means there are 8 eigenvalues and 8 eigenvectors. If you were to plot those eigenvectors, their plots would be mode shapes of deformation. And in this case, the first 3 mode shapes of deformation are not actually deformation. They are translation in y, in x, and rotation. So all these 3 are rigid body modes, and the corresponding eigenvalue of these 3 modes is going to be 0. Um, these next 5 are deformational modes if you use the full integration rule 2 cross 2. If you use a reduced integration, then these 2 modes, the reduced integration is 1 cross 1, and if you try to calculate the j at this point, you will see that the change in area, this element cannot detect the change in area because this is a trapezoid which is equal in area to the original square. So if you use one integration point, it cannot detect a change in area like this. So the element, if quote unquote thinks that there's no deformation like this, that it requires no energy to deform an element like this or like this. So this becomes a zero energy mode, which is also called an hourglass mode. So in addition to the 3 rigid body modes, if you use reduced integration, you can get these instabilities in your mesh. And actually, if you run a case with Abacus, you will see that these kinds of instabilities show up. In Abacus, this element is called, I think, CPS, which is called continuum plane stress 4-noded element with reduced integration, CPS4R. Okay, which I'll show you hopefully this week. So for small meshes, there can be these kinds of instabilities that will come up if you are using reduced integration. So that is again something that you need to keep in mind. All right, so let's take a look at what are all the steps of computer implementation that you will have to code up for a Q4 element. So just like before, if you remember from your constant strain or constant stress triangle, the input to that element subroutine was the coordinates of the nodes. If I give you x1, y1, and all those 4 coordinates, and if I give you the corresponding material properties, which in case of heat conduction would be conductivity matrix, and 2D elasticity it would be the D matrix. Then, and I also will give you the domain term, which in case of heat conduction is going to be body heat source. So everywhere in the element there could be a heat source. In 2D elasticity, it is a body force. And similarly, the boundary terms, it could be tractions or edge heat source in heat. So if I give you all this information, how do you calculate your element stiffness matrix, and how do you calculate your element force vector? That is something that you would have to code up for a general Q4 element. All right, so the first step is, now that you have the coordinates of the elements, these are the coordinates of the actual element. You want to find out what is the map that goes from a parent element, which is -1 to 1, to the actual element. And that map is given by the shape functions. So you will find the shape functions These are n hat alpha, which are functions of xi and eta. So actually, the first thing that you should do is determine what integration you want. So let's say we have chosen that we want to do full integration, 2 cross 2. So what we have chosen is that there are 4 points, let's say 1, 2, 3, 4, and we are going to calculate, or we are going to start a loop over all these 4 points. So what we are going to do is calculate the integrand at this point, multiply it with this area, integrand at this point, multiply with this area, and so on. And finally, we'll just sum them up and add them to our element stiffness matrix. So this is something that that will require a few loops to do. So the idea is that you will first calculate your shape functions, all the shape functions for each of the 4 nodes. Alpha is the node number. You will calculate all the 4 shape functions, let's say at this point. So in this case, Ci and eta j, both are 1 and 1 here, or plus and minus 1 upon square root 3. That's the 2 cross 2 Gauss integration rule. Okay. So at this location, you calculate the value of the shape functions, the 4 shape functions. You calculate the value of the derivatives. These things will not change for any element in the mesh. These things are remain constant for all elements in the mesh, right? Because these are over the parent domain.
The support has to be 1 over square root of 2.
If you are using a 2 cross 2 integration rule, then the point has to be 1 over square root 3. Right? This is minus 1 over square root 3 in Xi and minus 1 over square root 3 in eta, this point. So all we are doing is we are calculating the value of the integrand at this point. So these things will not change for different elements, but these will change from one point to the other. Okay, so that's why we have a loop over all the integration points. And once you have your shape functions, you can go ahead and calculate your J matrix. J matrix is nothing but dx, dxc, dy, d eta, and the off-diagonal terms. And to calculate all these terms, we saw maybe a couple of lectures back that what you would need to do is express x. So you would have to express x as this. This is the isoparametric map that you are using to denote what point does Xi and eta go to in the actual domain. So if you pick a point, this point, where does this go to in the actual domain? This is your isoparametric map. If you take the derivative of this x with respect to Xi, you will come up with this. Actually, this should be x alpha. So you guys remember that? Or okay, I guess I'll have to go back and right here. So the idea is that you can find out the location of x corresponding to any Xi and eta using the nodal coordinates. If I have all these nodal coordinates x1, x2, x3, x4, the 1 cross 1 Gauss point, the 2 cross 2 Gauss point is right here. It will map to some point here. And that map is going to be given by the same n matrix and the d vector that we had before. So instead of the d vector, we are going to just use these element coordinates, the vertices of the element. So once you have calculated your shape functions and shape function derivatives, you can calculate your J matrix. These are all things that you can calculate purely from the element coordinates. Once you have J, you can calculate its determinant. That's a one-line statement in MATLAB. Inverse of J, that is another one-line statement in MATLAB. And calculate your derivatives with respect to the actual coordinates. So these derivatives are with respect to the parent coordinates. These derivatives are the ones that we need for our B matrix. So these derivatives will be calculated with J inverse transpose times these derivatives. So this is something that we have talked before, but these are the steps that you would need to implement in your code. And finally, you will need to construct the n matrix, which in this case is going to be 2 cross 8 because 4 nodes. So there will be this sort of a structure for each node. And the B matrix, you can use these derivatives, which are right here. So another thing to point out here is that for the shape function matrix n, you do not distinguish between the parent coordinates and the actual coordinates. You can see that these are in black, these are in blue. What that means is for the shape functions, the value of the shape function at this point is going to be exactly the same here and here, but the derivatives are not going to be the same. That's why these shape function matrices, you can calculate the shape functions over the parent coordinates, but the derivatives you have to calculate over the actual coordinates. And then finally, once you calculate your B matrix, you can simply calculate this quantity. Now this is all at one Gauss point. So this is all being done at this one Gauss point right here. You will find B transpose dB, multiply it with your J determinant of J at this Gauss point, multiply it with the two weights. So what are the two weights for the 2 cross 2 Gauss point? If I have one Gauss point, that weight was 2, that was the length of -1 to +1. And if I have 2 cross 2 Gauss points, both Wi and Wj are 1. So the location of this point is minus square root 3, minus 1 over square root 3, and minus 1 over square root 3 in C and eta. And the area of this rectangle is actually a square, 1 times 1. Those are the weights in the C and eta. So you will take all that, add it to your k element stiffness matrix that is just 8 cross 8. And this is all at this one point, all at this one point. And then you will repeat this entire procedure, A, B, C, all this D up to whatever F. All these 6 steps for this point, then all those 6 steps for this point, this point, this point. And within each of those 6 steps, like for this case, at the step 1, there is n alpha, which needs to be repeated for all the 4 shape functions. So isoparametric elements can be really quite expensive to calculate when you're doing your MATLAB calculations. If you have even 1,000 elements, or even maybe a bigger mesh, let's say 10,000 or something like the mesh that I gave you, 2,000 elements, that will and if you're doing this 2 cross 2 integration, that will take quite a bit of time to calculate. It will not be as fast as your CST elements. But essentially this is all just coding up stuff. So and what you need to understand is how this is all going back and fitting together in the original weak form. So this is how you would calculate your element stiffness matrix. The same thing for your element force vector. You already have your n matrix. This is your n matrix. Multiply it with your body force vector or your heat source term. Multiply it with your determinant of J, calculate it at all the 4 Gauss points, multiply it with the weight, and keep on adding it to F for all the 4 Gauss points. So this is all your numerical integration. So that was the loop for the domain term. Now you still have the loop that you have to construct for the boundary terms. So let's say you have tractions on some edges of the boundary. In this case, let's say there is traction on only one edge. So in the figure that I've drawn on the previous page, we see that the traction is on this edge, and this edge is going to map to this edge. But in general, if you are trying to calculate the tractions at all the four edges, you would have to loop over 4 times all those 4 edges. And in this case, again, for each edge, let's say we choose 2 Gauss points. So the Gauss point location, this one would be Ci, that is plus and minus 1 upon square root 3, and eta would be -1, right? So that's why we have this as the choice. We do all the previous steps that we did for the boundary terms. We need to do them again for this boundary term. So all the steps that we did for the domain term at those 4 points, we need to do them again at these boundary Gauss points. So calculate J just as before, calculate the shape functions and the derivatives as before, calculate J as before, but for the boundary terms, instead of calculating the determinant of J and the inverse of J, what we need is actually the length factor. So if you look at maybe 3 or 4 lectures back, there was this length factor that we needed to integrate, and maybe I should show you that. Right, this one. So if you remember, all the boundary integrals, we needed to calculate something on the integral of the along the boundary of the element. So we said that this dl is dx dy, and we needed to calculate this quantity for this edge. And similarly for edges 2 and 3 and 4 and 1, which are this and this, you needed to calculate a different length factor. So this length factor is measuring nothing but what is the length change from here to here. And that is the length factor that we are trying to calculate right now. So that length factor, I'm denoting that with JL. Once you calculate that, construct your N matrix at this point and calculate your boundary term, keep on adding it to the element force vector. So in case you have tractions on all the 4 edges, and you are using 2 cross 2 Gauss points, then how many times will you have to run this loop? If you have tractions on all the 4 edges, you are using 2 points per edge. How many times will you have to run this loop? So 4 times for each of the 4 edges, and twice within each for the 2 Gauss points. So again, for the body term, domain term, you had 4 Gauss points. So you had to run the loop 4 times, and at each point you would have to calculate 6 steps. In each of those 6 steps, you have 4 shape functions. In this case, if you have 4 edges, 2 Gauss points per edge, you would have to calculate 8 times, and you would have to repeat all these 5 or 6 steps at each of those 8 Gauss points along the edge. So it can get a little expensive, but in terms of coding, it is not a problem. You just keep on doing a loop, nest another loop inside that, nest another loop inside that. So in terms of coding, it is not a problem, but it will take a lot of computational time to do these kinds of calculations. All right, so at the end of this, once you have calculated all your body force, all your body terms, and calculated all your boundary terms, domain and boundary terms, at that point you should have your correct element stiffness matrix. And again, these are all estimates. These are approximate K element, approximate F element. This is different from CST, where in the 3-noded triangle, you had the exact K element and the exact F element. But if you have distortion in your elements, these will not be exact. These will be approximate. So these are basically the steps for implementing a general Q4 element. So in the little bit of time that I have now, maybe I'll just introduce this today, and then we'll continue next time. So we've looked at triangular elements, we've looked at rectangular elements, but we have only looked till now where shape functions are linear, or at most bilinear. Okay, And as we saw, as you saw in your homework 5, that if you use a linear triangle and if you use a coarse mesh, you do not get an accurate enough answer. Okay, so the way that we did, the way that you did in your homework right now to get a more accurate answer was to increase the number of elements. Instead of increasing the number of elements, what you can also do is increase the order of polynomial within each element. So going back to, let's say, something like this. This is one three-noded triangle. Instead of chopping this domain up or dividing this domain up into many more smaller three-node triangles, I can choose the same mesh but add nodes within each triangle. And if I do that, what I will get is something like this. So this is a quadratic triangular element where we have added these three nodes which are exactly in the middle. So this is another constraint with triangular elements, that when we add nodes to a triangular element, we add them exactly in the um, that are equally spaced along the three edges. So for the quadratic element, we add these three nodes in the middle. And if you see, what would be the order of polynomial if I use these 6 nodes now? So if you remember, the order of polynomial for the three-noded triangle was linear because we have 3 degrees of freedom at in total. 3 degrees of freedom, let's say for the heat conduction, for a scalar problem. We have 3 degrees of freedom at 3 nodes. We can approximate any linear function using 3 nodes. If I have 6 nodes, I can go up to 1, 2, 3, 4, 5, 6. I can approximate any polynomial that is quadratic exactly with a quadratic with a 6-node triangle. Okay, and similarly, you can keep on increasing this number of nodes in the triangle. So in this case, if you have how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 nodes in this triangle, and in each along each direction you have a cubic polynomial. So if you there are 10 nodes, which means you will have 10 degrees of freedom total, 10 scalar degrees of freedom for this triangle, which means that you can approximate a polynomial that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to t. So t10 element will approximate up to cubic polynomials over the domain exactly. And similarly, you have this quartic polynomial, and you can keep on increasing this order. And this type of a triangle, this type of a triangular representation of polynomials is called a Pascal's triangle. And we will see also in rectangular elements that that some of the terms are not approximated with rectangular elements. So you will see later on that, for example, the bilinear rectangular element Q4, that had terms like 1, x, y, and xy. So that had these 4 terms, which means that it was not complete in the quadratic term. Okay. Um, so another good way of actually coming up with shape functions for the triangular element is using area coordinates. And let me just briefly tell you what this is. So in area coordinates, let's say you have a triangle like this, and instead of using xy coordinates to express shape functions, what we use are area coordinates L1, L2, L3. So these are not 3 independent coordinates. These are actually dependent. They are related by this relationship L1 plus L2 plus L3 is 1, which means that there are only 2 independent coordinates, x and y. And what they mean actually is, let's say for L1, you find the area of this triangle and divide that by the area of the total triangle, that's L1. Similarly, you have this L2, this triangle, green, divided by the total area, that is L2, and which means L3 is going to be whatever is remaining. So that gives you this relationship. So next time we'll see how to come up with the shape functions using these area coordinates. All right, so see you all Wednesday.